Okay, welcome to this week's HoTT. We are happy to have Axel Ljungström from the University of Nottingham. He will be telling us about a formalization of the Serre finiteness theorem. Please go ahead.
Okay, hi. Thanks for having me. So this is a presentation about a formalization. So this is a formalization that's based on work by Reed, Barton, and Tim Campion, but the whole formalization project is kind of a joint thing with Reed, Owen, Anders in Swedish, and Loic Pouget. Right. So here's just a little bit of introduction for those of you who don't know what this is all about. So as some of you know, homotopy groups of spheres are kind of fundamental if you're a homotopy theorist. So you could argue that they're kind of the very building blocks of homotopy theory in some sense. Now, unfortunately, they're very hard to compute. And I mean then compute, well, both computers in a computer scientific sense, but also in a mathematical sense. They're hard to characterize. So imagine if there was a formally verified algorithm which could quickly compute these homotopy groups. Wouldn't that be amazing? But then you remember, we're working in homotopy type theory, so wouldn't it be amazing if there's a formally verified algorithm which, at least in theory, could compute these, and perhaps not so quickly. So that's kind of the topic of today's talk. Well, there's an equivalent formulation here. Imagine if there was a formalization of the Serre finiteness theorem in Cubical Agda. And that's what this talk is about. So announcing there is one. Okay, so what is the Serre finiteness theorem? In order to be able to state the sort of more general version that I'm going to present today, I need a concept called stably almost finiteness. For now, let me just black box this definition. So I have I hope you're okay with Agda syntax. I'm doing a little experiment in this talk. I'm kind of mixing maths and Agda notation. We'll see if you like it or hate it. But for now, we're going to postulate this stably almost finite predicate. And the Serre finiteness theorem, as proved by Barton and Campion in HoTT, formalized by us, says the following. So if you are given one connected and pointed type X, if this type is stably almost finite, then pi n is finitely presented for n greater than or equal to 2. So in particular, spheres in dimension greater than or equal to 2 happen to be stably almost finite and one connected. And in lower dimensions, we know what their homotopy groups are anyways. So we get this nice corollary from this theorem, which is kind of the coolest form of it if you like homotopy groups of spheres. Pi n of Sm is finitely presented for all n and m. And this makes sense because this is actually a group for all n and m. So yeah, that's a pretty big theorem. So the goal of this talk, so it's always hard to give a formalization talk because I can't just show you a bunch of code and I mean, you want to get some math out of it too, probably. So I'm going to try to give you a rough idea what the proof of Barton and Campion looks like. But in order to do so, I need to start with some basic definitions. And this is always hard because I never know. Some people are new to HoTT and some people are not so new to HoTT. But just very briefly remind you of just what is the definition of a homotopy group. So a homotopy group of a pointed type X is just maps from the n sphere into X, or pointed maps from the n sphere into X. And you take the set of such maps. You can also define it as the nth loop space if you know what that is, but that whichever definition you pick doesn't really matter. Also, I'm going to remind you of the concept of connectedness. So a type is said to be n-connected if its n truncation is contractible. And a fact here is that X is n-connected implies that pi k vanishes for X smaller than n. And there's also a notion of connectedness of functions. So a function is n-connected if its fibers are all n-connected as types. And the key thing here to take away is that if a map F is n-connected, then it induces an isomorphism on homotopy groups in dimension k greater than or equal to n, and it happens to be surjective, at least in dimension n minus 1. I think those were the only sort of basic definitions. Okay. Also, here's maybe a less common one, but that's easy to state. So given a pointer type X, we can define its n-connected cover. Yeah, it has to be. Yeah. We can define its n-connected cover, denote like this, xn. And we define it to be the fiber of just the inclusion or the truncation map, going from X into the n truncation of X. So in particular, you have a nice fiber sequence like this. So why are these guys nice? Well, first of all, the xn, as the name suggests, happens to be n-connected. Second of all, if you compute pi n of xn minus 1, this happens to be the same thing as pi n of x. So things are easy to prove. So a conclusion here is that if you're interested in computing pi n of x, you can always just replace x with its n minus 1 connected cover. And then you get to compute something which is kind of like x, but it has the additional property of being n minus 1 connected. So that's a sort of a nice trick. And that's kind of the key idea of the Serre finiteness theorem proof by Reed and Tim. Okay. Right. So let's recall what the main theorem said. So we're saying that given an x one connected pointed type, if it's stably almost finite, whatever that means, then pi n of x is finitely presented for n greater than or equal to 2. So the idea of the Serre finiteness theorem proof is very simple. We want to know pi n of x, where x is stably almost finite and 1 connected. This would be easy in a bunch of inverted commas if we knew that x were n minus 1 connected and stably almost finite. And this follows from my results, which we proved in another paper by myself and Loïc Bouget, which I'm going to talk about later. For now, just accept this fact. Well, then there shouldn't be a problem, right? All we need to do is just replace x with its n minus 1 connected cover and apply this theorem, whatever that it says, and we should be done. Well, there's one detail, and that is we need to know, of course, that taking the n minus 1 connected cover of x still gives you something that's stably almost finite. So we have kind of reduced the main theorem now to these two theorems. So theorem A, if x is stably almost finite, and as a technical condition, 1 connected, then x of n is stably almost finite for any n greater than or equal to 1. And theorem B, if x is stably almost finite and n minus 1 connected, then pi n of x is finitely presentable. So I hope you can see that these two theorems together imply the Serre finiteness theorem. And these two theorems kind of guide the entire formalization as well. So the formalization project started with us trying to nail down this theorem. That was especially the people at CMU doing that, and the Stockholm people were kind of then trying to get this theorem proved. Okay, but let's start with focusing on theorem A. So that's the first part of this talk. Right. So time to address maybe the elephant in the room. What does it mean for a type to be stably almost finite? So this was one of the first things that was formalized, and this was primarily done by Owen at CMU. And the definition of this uses finite CW complexes. So we will do some more black boxing now because I don't want to specify what a finite CW complex is yet. But this is actually what we did in the formalization. So for a long time, we had this thing in the formalization. So we had a postulate saying that there's a family of predicates over types, which express that they are finite CW complexes. And in particular, we have some extra properties. For example, finite sets are CW complexes. If you take two maps, F and G, where all of the types involved are finite CW complexes, then also their pushout is a finite CW complex. And if you take a family of finite CW complexes living over another finite CW complex, then the sigma is a finite CW complex. So you have these closure properties that we assume. And this is kind of how we worked in the beginning of the formalization as well. So for now, this would be the definition of a finite CW complex. Okay, let's move on to stably almost finiteness. Oh, right. Yeah, I will write fin CW for the universe of all finite CW complexes. So types that are equipped with a finite CW structure. Okay. Yes. Okay. So, okay. I hope you're okay with the Agda notation now. This was a little experiment. I wrote everything using regular maths first, and then I switched to Agda to make it look cooler. This is not at all from the formalization. This is completely fake, but I thought it looked cool. You can tell me later what you think. Okay, so what's an n-finite type? So is n finite x? So x is an n-finite type. This is going to land in H-prop. So we say that x is n-finite if there exists, so merely exists, a C in the universe of CW complexes. Sorry, I should say finite CW complex here, I think. Well, it actually doesn't matter. Anyways, together with a map from C into X, such that this map is n-1 connected. Now you can actually beef up this definition a little bit. This is completely equivalent. We can add an extra field just for extra information. We can also assume that our CW complex is itself n-1 connected. This is equivalent to what I had before. So this will be our definition of a type being n-finite. So n-finite x being n-finite just means that x kind of looks like a CW complex if you look at low enough dimensions. In particular, lower homotopy groups will be the same as those of and homology groups too will be the same as those of a finite CW complex. Okay, I'm going to write suspension hat for iterated suspension, and that will be used now to define what's called stably n-finite types. So we say that x is stably n-finite if there exists an m natural number such that the mth suspension of x is n plus m finite. So, you know, being stably n-finite means it's kind of n-finite. You just have to suspend it enough times and then it becomes, well, n plus m finite. But it's finite up to suspension in a sense, right? And then we get to the definition of stably almost finite types. So we say that x is stably almost finite if it's stably n-finite for every n. So what's the point of this strange-looking definition? Well, so the intuition here.
Axel, could you flip back?
Yeah.
I'm still trying to parse this slide.
I'm sorry.
So I'm still looking at the is n-finite definition.
Yeah.
You said you can add that last field and it doesn't change anything. But it seems to me that I don't know, I guess I was a little surprised by that. Can you explain that?
Well, I mean, so the idea is that instead, if you have a CW complex C, you can just take yeah, it says actually a mistake. Is this where we add this?
Doesn't that condition...
Owen is here.
Hello. Do you possibly mean is an n-1 dimensional CW complex?
Thank you. Yeah, this is what I should say. Yeah.
Okay, because the map F is an equivalence in low degrees. So if you force C to be connected, then X would have to be connected.
Yeah. Right? No, this is a mistake. Yeah.
Okay.
And now I'm a little bit worried that this might appear in the future, but now we're aware of this of this appearing. It should say n-1 dimensional, or is it n dimensional? Well, n plus minus.
Okay.
Constant.
And then could you just quickly go over the rest of the slide again? Because this seems to be very important.
Okay. Okay, so we have this, well, okay, but let's just ignore that field. So just take this to be the definition, and then, so this is just suspension. So spend n times. So we say that a type X is stably n-finite if there merely exists some m, such that if you suspend x m times, then the result is n plus m finite. And then we say that it's stably almost finite if this is true for every n. So for every n in the natural, x is stably n finite. Hope that's okay. Okay.
Great, thanks.
Is there an intuition behind calling this almost?
Well, I guess it's well. So so I should say that this is from the paper by Tim and Reed. So I don't know what intuition they had behind it.
Yeah, maybe I can comment on that. If you
yeah,
can
yeah,
hear me.
Yeah.
So I guess one way to think of, like, for example, being stably n finite is sort of like the suspension spectrum of X looks like the suspension spectrum of a CW complex through degree n or so, right? Because at some stable condition now, it's preserved by shifting X by 1. And then stably almost finite, the term comes from ultimately some kind of maybe homological algebra notion. So if I might have for example, a module of a ring, and a module might have a finite projective resolution by finitely presented projective modules or something, then that's a very strong finiteness property on my module. But there's like a slightly weaker property, which is that for any n, I can resolve it by projectives through degree n, using only finitely generated projective modules. And this is sometimes called, well, in Lurie, it's called being almost finite. And sometimes it's called being, I think, quasi-finite or something along those lines. I don't remember exactly. That's where the terminology comes from originally.
And I think
so it's sort of finite. It's not finite all the way out, but any finite dimensional part of it is finite, so to speak.
And I think the point is that the CW complexes are supposed to be finite CW complexes in the main definition. So that's where the finiteness is coming in.
Yeah, that's absolutely right. Yeah.
Yeah.
You know, stably almost finite CW type, really.
Yes. Okay. Well, yeah, I guess this is somewhat related to what we just said. So at least my intuition for what the stably almost finite types was purpose they fill is that their homology will clearly be finitely presentable. So that's because, well, if you take the Hn of X for any n, and this is where the any n in the definition of stably almost finite kind of refers to, in a sense. If you take Hn of X, then you can always suspend that m times, and you get an isomorphism between Hn and Hn plus m. This is stability. And then this guy will have the same homology as C for some CW complex, and this because we have a sufficiently connected map that's going to induce an isomorphism on homology, and this latter group would always be finitely presented if you use a cellular homology theory. For example, it's easy to, I mean, it's trivial to show that. So that's kind of the intuition for me. So the intuition for me is that stably almost finite types behave like it's kind of a homotopy theoretic version of stability of homology theory, in a sense. Well, that was not really a sentence, but you see where I'm going with it. Okay. So yeah, so it kind of turns out that in their proof, since they kind of use this language of stably almost finite types all the time, they never actually have to refer to kind of a concrete homology theory. So that means in particular that the proof of the Serre finiteness theorem never has to mention homology explicitly at all, which is kind of cool. Right. Okay. So I guess I'll just briefly run through this. So the goal is to prove that n connected covers of n is of a stably almost finite type is again a stably almost finite type. And this would be deduced by via a bunch of sort of closure properties of stably almost finite types. So it kind of all starts with this lemma, and I'm mentioning this lemma in particular because the proof relies on something that I'm going to return to later. So for example, we have the co-fiber closure. So if given a map F, from X to Y, where X is n-1 finite and Y is n finite, then the cofiber of F will also be n finite. And now I've probably made the same mistake as Dan pointed out before. Let's see if I have. Okay, so we get a diagram like this, a map F going from X to Y, and then we have two spaces here, XC and YC. So here XC and YC are CW complexes, and this map FC can be deduced to merely exist via a connectedness argument. And you can also show that this guy has to be n-1 connected. So of course you get an induced map on cofibers. And this map happens then to be n connected instead. Yes, am I off by one now in my, anyways, plus minus one for the ends here, but we conclude then by noting that the cofiber of this map, well, it's a cofiber of a map between CW complexes. So that's again a CW complex, and that's kind of what you need to show. So using the closure of CW complexes under pushouts, you have proved that the cofiber of F is also n finite. Because this is CW complex. I think I'm off by one here. Regardless, I just wanted to point this out because this property here is, I mentioned we postulated it before, but this is kind of it's actually a pretty annoying property to prove, and that's something that we focused on in the paper with Loic that I'm going to return to later. Okay. Yeah, okay, but now we know that suspensions commute to cofibers. So from the previous lemma about sort of cofibers preserving n finite types, we're going to get the corresponding lemmas for stably almost finite types. So given a map F from X to Y, where X and Y are stably almost finite, we get that the cofiber is stably almost finite. Very easy consequence from the previous result. And even better now is without the Agda notation because it was too ugly to write out. If you're given a cofiber sequence, X, Y, Z, so Z is the cofiber of F. If any of these two types are stably almost finite, then so is the third. And you can use these results to prove further results about stably almost finite types. So for example, you get the Cartesian products, wedge sums, smash products, and joints are all of stably almost finite types are all again stably almost finite. This is kind of a nice class of types. Okay. So we proved a bunch of properties for co-limit constructions now. Well, we didn't prove anything. You saw a list of lemmas. But what we actually want is we want closure properties for, well, more limit-like constructions. So we want, for example, fibers and loop spaces, because in the end, we want to prove that taking n-connected n-connected covers of types preserves stably almost finiteness. So we really want to show that they preserve a bunch of limit properties as well. And the kind of key construction or theorem for translating these results into sort of limit properties would be the Ganea construction. So this is a classical result from, I guess, the 50s or something. 50, yes, something, which due to Ganea, of course. So if you're given a fiber sequence, FEB, where I would be pointed, I don't know why I pointed that out. There's a fiber sequence associated to this guy going from F join loop space of B into the cofiber of J into B. And so this was formalized twice, I think, once by me and once by Owen, I think. In the end, we went with Owen's formalization. And what's the point of this guy, of this theorem? Well, if we apply Ganea to this sequence, we get a new fiber sequence, loop space B into some cofiber into B. And then you can apply Ganea to this sequence again, and you get a fiber sequence with 3 copies of omega B here, some cofiber here, and some B here. And you can continue doing this over and over again until you get a big join of loop spaces, some space En, which is some kind of iterated cofiber mapping with a map into B. And if we also assume that B is connected, then this map would be n-1 connected. And sort of using this sequence, playing around with this sequence, you can deduce basically all of the results on the following page. So you just have to apply this sequence in clever ways to, and you get all of these nice properties. So in what follows, B is going to be always going to be connected, and we fix this fiber sequence here. So first lemma, spaces with stably almost finite loop spaces are stably almost finite. So if omega B is stably almost finite, then so is B. And you get the same thing in the other direction if you add the assumption that B is actually 1 connected. And all of these results are just by sort of playing around with the Ganea construction and using the previous properties. For example, the joins of stably almost finite loop spaces, stably almost finite types are stably almost finite. Just combine these results in nice ways, and these things kind of fall out. Now, this result here also implies that KGN is stably almost finite if G is finitely presentable, which is an important result, which I guess I'll leave as an exercise. Also, you get these sort of 2 out of 3 like properties. Well, kind of. So if B is stably almost finite and omega B is stably almost finite, then so is E. And if B is 1 connected and E is 0 connected, B is stably almost finite and E is stably almost finite, then F is stably almost finite. So that's nice too.
Sorry, for the second last one.
Yeah, I was I think this should be for the. Did I forget? Oh yeah, I think if stable almost finite F should be in here probably.
Yeah.
Otherwise, it would be pretty odd. Well, yes, thank you. See, this is what happens when Eduroam crashes before you're about to give a talk. You don't have time to spot these things. Okay. Well, now let's restate the sort of first key theorem that we wanted to prove, theorem A, and now with this cool Agda notation, just to make you really understand that this has been formalized. Although clearly there are some mistakes in my pseudo Agda code. So theorem A, given any natural number greater than 1, if x is, again, I think 1 connected, if x is stably almost finite, then its n-connected covers are stably almost finite. And this is now, the proof here is really nice. So Tim and Reed prove it by showing that the n-connected covers and the n-truncation both are stably almost finite, and you do this mutually. So you do this by mutual induction on n. And the only thing you really need is these 2 fiber sequences combined with the previous lemmas about fiber sequences preserving stably almost finiteness. So you just look at this fiber sequence where you have an Eilenberg-MacLane space over pi n of x here, and you have the map from the n truncation into the n-1 truncation here. And you have the defining fiber sequence of n-connected covers here. And sort of by induction, since this is stably almost finite, you can prove, I guess, that this one is stably almost finite and this one, and yeah, you kind of you go this way. You combine these 2 sequences in a nice way, and the proof is very pretty. But you'll have to wait for them to publish a paper until you can read it. I don't want to give too many details, of course. Okay, so that's the big first theorem. So this was sort of the big first milestone in the formalization. So far, the formalization includes definition and theory of finite CW complexes, but well, this has only been postulated actually. Of course, there's a bunch of theory about stably infinite and almost finite spaces, which includes then a lot of connectedness lemmas, closure under cofibers, just the formalization of cofiber and fiber sequences is tricky, actually. Of course, the Ganea construction takes time to formalize. So I tried to estimate how much code this consisted of, and I got it to be around 8,000 lines, with some of this code already being in the Cubical library, so that's excluded from these 8,000 lines. So it's a significant amount of code. Okay, so that's the first part. So let's go back to the main proof. So what we showed was if x is one connected and stably almost finite, then so is xn for any n greater than or equal to 1. And we also know that pi n of x is the same as pi n of its n minus 1 connected covers. And in the end, what we want is if x is stably almost finite and 1 connected, then pi n of x is finitely presentable for n greater than or equal to 2. I think this is the third time I mentioned the main theorem we're trying to prove. So, well, using this knowledge, we just want to show theorem B. So I'm just reminding you of theorem B here. If x is stably almost finite and n minus 1 connected, then pi n of x is finitely presentable for n greater than or equal to 2. Okay. So we're at theorem B now. Well, let's inspect the premise of the theorem further. So we in the premise of this theorem, we assume that we have an an n minus 1 connected pointed type x. But that means that if you take pi n of x, that's going to be the same as pi n plus m of the mth suspension of x. And this is by the Freudenthal suspension theorem. And that's because we assumed that n was big enough, of course. Now, x is stably almost finite. So that means that tells us by definition that we can find an m here such that pi n plus m of the mth suspension of x is pi n plus m for some yeah, so in this case, it actually makes sense to take the CW complex to be n plus m minus 1 connected, right? Okay, ignore this comment here. Well, for a CW complex. Yes. Okay, now I'm confusing myself.
Now this is funny because x is already n minus 1 connected in this case. So.
Oh, thank you. Yeah, of course. Yeah. Yeah. We're suspending an n minus 1 connected type m times. So of course we can also assume then the C is n plus m minus 1 connected, since that's the same level of connectedness as this thing. Yes. So this is fine. Thank you, Reed. So if you put these things together, you see that the only thing you actually need is if you're given C, an n minus 1 connected CW complex, then pi n of C will be finitely presented. So I'm calling this the weak Hurewicz theorem, and I will tell you why now. So of course, if the weak Hurewicz theorem is implied by the full Hurewicz theorem, which was of course proved in HoTT by Dan and Luis Kokora. So we could obviously just formalize this one, and that was the original idea. So we didn't do so well because for 3 reasons, I guess. We hadn't already done it, so we were lazy. But actually, if you only use the weak version never mentions homology at all. So this idea of getting if we want to produce a completely homology-free proof of the Serre finiteness theorem, which, well, I don't know why we want that. It sounds kind of cool. Then if we use the weak one, using the weak one would be the way to go. But the main reason is actually that this weak version of the theorem was already kind of about to be formalized by myself and Loic, almost by accident in our project on CW complexes. So I now want to change the topic of this talk a little bit. Well, I'm going to stay close to the Serre finiteness formalization, but I want to talk about my project with Loic now on CW complexes. And this is because this sort of one of the main theorems we prove in this paper is this weak Hurewicz theorem. So part 2 of the talk, CW complexes and the Hurewicz theorem. So this is all about my paper with Loic. So a bit of history first. So I think it was 2023. So Anders Mörtberg, my supervisor at the time, at least, gets a new postdoc, Loic Pouget. And Anders has this idea for a project. He wants to define cellular cohomology and homology to simplify Bruneri number computations. And the idea is to put me and Loic on this project. Then Anders goes on parental leave. So Loic and I decided that this would be a good time to develop some key theory behind CW complexes, because we're going to need that anyways at some point. You know, basic things like push-outs and suspensions and whatnot. So our goal here was to develop enough theory about CW complexes in order to be able to prove the Hurewicz theorem. And I mean, the Hurewicz theorem had already been proved in HoTT. This was more of a sanity check for us. It's sort of, if we know enough about CW complexes and cellular homology to prove the Hurewicz theorem, I think, you know, that's a sign that we've set things up correctly. So this was kind of a long time goal for us. Now, so Swedish parental leave is quite generous. So Anders was away for a bit longer than I think Loic and I anticipated. So we ended up getting quite far in this project and actually ended up writing a whole paper on these developments by the time that Anders was back. So when Anders comes back, he gets me more involved with the Serre finiteness project, and he reminds me that Reed and Owen, they need a version of the Hurewicz theorem. So I show this draft with Loic to Reed, and he spots this weak Hurewicz theorem, which we hadn't even thought about. You know, I mean, we never thought this was interesting at all. It was kind of just part of the proof of the real Hurewicz theorem, but it was kind of hidden in the proof. Also in the formalization of this, it was kind of hidden in a big where clause. But Reed notices that that's exactly what's needed to complete the Serre finiteness formalization. And ends up kind of rewriting the proof actually, so that it uses only this weak version and kind of never mentions homology at all. Okay. So in addition to what I've mentioned already, so Loic and I do a bunch of stuff in our paper. The key contributions are like, well, a workable definition of CW complexes, basic constructions like push-outs of CW complexes, and something that we call the Hurewicz approximation theorem, which is a characterization of low-dimensional skeleta of unconnected complexes. And this Hurewicz approximation theorem plus computation of certain homotopy groups will give us this weak Hurewicz theorem. We also prove a bunch of stuff about cellular homology, but as I said, we're not going to need that today. So let's take a quick look at what me and Loic did. So I'm back to my pseudo Agda code. So we went for a definition of CW complexes where, well, we went for a non-recursive version of CW complexes, I should say. So we first define what a CW structure is. So a CW structure will be underlying, I should say here. You first have an underlying sequence of types, so a skeleton or the skeleta. And then you have these maps going from the n skeleton into the n+1 skeleton. So it's just a sequence of types with maps between them. And then for each natural number, you have the number of cells in that dimension. That's cell size here. And you have these attaching maps that go from, for each n, they go from the n-1 sphere cross fin, where fin is the size of, well, is the number of cells we want to add, and it maps into the n-1 skeleton. And so this is just the data kind of defining a CW complex, and then you need this data to satisfy some axioms. So the first axiom is that the -1 skeleton, which we introduced for technical reasons, this has to be empty. And we also say that the n skeleton has to be equivalent to the push out of the attaching map along the second projection here. So as in this diagram. So we have the attaching map here, and we have the second projection up here. And this should take you from the n-1 skeleton to the n skeleton. So this was our definition of CW structures. And then we use this to define finite CW structures. So we define, we say that X is a finite CW structure of dimension n if for every m greater than n, the map iota is an equivalence. So the map iota here, just to remind you, is the map going from the n skeleton to the n+1 skeleton. So basically, what we're saying here is that if all the maps in the sequence defining our CW complex at some point start becoming equivalences, then it's finite. And this is nice because its equiv is an h-prop, so it gives us an h-prop without having to truncate anything. And then we say that a CW structure is finite if there merely exists an n such that X is finite of dimension n. Okay. Right. So that's a finite structure. Okay, so what's a finite CW complex? Well, a type is a finite CW complex if there merely exists a CW structure such that this CW structure is finite. And if you take the co-limit of its underlying sequence, that's equivalent to X. And then we can form the universe of all finite CW complexes. You just say all types such that all types A such that A is a finite CW complex. So, they're a bit round about these definitions, but they turn out to be quite flexible. We played around with other ones too, but I can talk about that more later if you're interested. Of course, we can remove all the finiteness assumptions here and to just get a nice class of non-finite CW complexes too. And actually, that's what we did. For a lot of the paper is written about about CW complexes, not finite ones, but theorem. Here's a theorem. Given a span of CW complexes B, A, C, where A is a finite CW complex and B and C aren't necessarily, the pushout is again a CW complex. And this pushout will be a finite CW complex if B and C are finite CW complexes. And you prove this by first proving a constructive version of the cellular approximation theorem. And the constructivity here is what forces A to be finite. Annoying, but such is life. And then you do a bunch of technical path algebra and you can prove it. I'm not going to do it here. But this, I highlighted this before. So this was a very sort of a crucial theorem in the Serre finiteness proof, actually, which was only postulated until now. But now we finally know that CW complexes are closed under pushouts. So that's nice. Okay. And then we define this crazy thing called Hurewicz structures. I think we call them good structures in the paper, but now I'm calling them Hurewicz structures. So X, CW structure X has a Hurewicz structure if for every m, so you fix an n, so it's a Hurewicz structure of dimension n, if for every m smaller than n, the m skeleton is contractible. So your CW complex just starts with a bunch of points up until dimension n. And then what happens in dimension n? Well, you get a finite set A, a finite set B, and you get a map from the wedge of n+1 spheres into the wedge of n+1 spheres. First one indexed by A and the second one indexed by B. And then we say that the n+1 skeleton is equivalent to the wedge of n+1 spheres indexed by A. And the n+2 skeleton is equivalent to the cofiber of this map, F, that we assumed here. So, this is just a silly record type, but we can assume that some CW structure X, that there's an N such that this X satisfies all of these things. And if a type does satisfy these things, so if there's an N such that a type X has a CW structure, such that this CW structure is Hurewicz, then I'm going to call it, I'm going to call this type Hurewicz connected. or Hurewicz n connected. This is perhaps looks unnecessarily technical, but it's just a different notion of connectedness. So it's just describing exactly what the lower cells, sorry, but the lower skeleta of the type look like. And what's the significance of this? Well, if X is Hurewicz n connected, then we merely have the existence of such a map that was assumed in the record. And we also have the pi n plus 1 of X is equal to pi n plus 1 of the n plus 2 skeleton. This is always true. But then in the record type we saw before, we also saw that X n plus 2 is the cofiber of F. So if X is Hurewicz n connected, you have that pi n of X is pi n plus 1 of the cofiber of some map F of this form. And we can compute the degree of such a map. So the degree of such a map F will be a Hom from ZA into ZB. I'm not going to develop this whole theory about degrees of such maps now, but there's such a theory. We can read the paper. And the theorem we prove is that if you take pi n plus 1 abelianized, just to be careful in the lower dimension, when n is equal to 0, ZB mod the image of this guy well, this guy is equal to ZB mod the image of the degree of F. And in particular, what this means, this is precisely what it means to be finitely presented, right? Well, not precisely, but this implies that this thing is finitely presented. Okay, and how do you prove this? Well, you do a direct computation when n is equal to 0, and then you do sort of a sledgehammer Blakers-Massey argument when n is greater than 0. It's a pretty neat proof. Okay, I'm running a bit low on time, but I think it's okay. Okay, so what we have proved using these results is this weaker Hurewicz theorem. Given X and n-1 Hurewicz connected with this weird definition I gave before, CW complex, pi n of X is finitely presented. So what we really need is this Hurewicz approximation theorem, which says a CW complex X is Hurewicz n connected if and only if it's n connected. And in particular, this direction, Hurewicz n connected to n connected is non-trivial. So this is one of the main things we prove in the paper. But if you have this, you see here what happens to this guy. He gets crossed out, and this guy gets crossed out, and we have suddenly our weak Hurewicz theorem proved. And that was precisely what we wanted to prove for the Serre finiteness theorem, right? Okay, and that's kind of it, right? So let's summarize the proof of Serre finiteness to just remind you of everything again. Let's put everything together. We took a type X, which was 1 connected and stably at almost finite, and we fix some natural number n. We note that pi n of X is pi n of the n-1 connected cover. X is stably almost finite. This implies that the n-1 connected cover is stably almost finite, and it's also happens to be n-1 connected. This means that pi n of x n minus 1, this is a typo, pi n of x n minus 1 is equal to pi m of C for some m minus 1 connected CW complex C. But this is finally presented by the weak Hurewicz theorem that we just proved. And we get the main theorem, which I don't think I need to read out again, since I think it's the 4th time now I state it. So that's the proof by Tim and Reed. So I guess I have roughly 10 minutes left. I wanted to mention, so I hope you kind of got an idea of what the proof looks like, but also kind of the order of the formalization and how things went about. So let me just mention some quick things about the formalization and some knowledge this has produced. So there are many silly lessons you learn when you formalize things. So even the implementation of types like thin will matter. a lot when you formalize things, especially about finite subsequences. So for example, we were working with finite subcomplexes of CW complexes, and we needed to rely on things being indexed by fin. And whenever you have something indexed by fin, you want certain equations to hold definitionally if you want to be able to avoid transport hell. So for example, these two ways of going from fin n into fin 2 plus n should be equal definitionally, one could hope. And this is, for example, true if you use the index inductive version of fin, which is very nice. But of course, Cubical Agda doesn't really support the index inductive version. Now, what about the standard definition? So just saying that fin n is the all m's smaller than n. Well, that only behaves nicely if this one is appropriately defined. So when we started the formalization, we used this version of fin. We said that m is less than n if there is some x such that suc of x plus m is equal to n. This turned out to absolutely break everything at some point, and we had to go back and rewrite the code and instead implemented this definition. So this is just the sort of obvious inductive definition of this guy into a map into H-prop instead. So these type of silly things you learn when you formalize things. Another thing that I learned was be universe polymorphic from the start. Don't prove things for types in the same universe. Just introduce all the universe levels possible whenever possible, even if it forces you to define the maximum universe level of a list of universe levels, which I ended up doing for one of the theorems. Lesson number 3. Well, this was a comment about our definition of CW complexes versus the recursive one that's also available to us, but I don't have that much time. So if someone is interested, I can talk about this later. Okay, same thing here. Encode decode is king. So we were able to avoid quite a lot of algebra by computing a Booleanization of fundamental groups directly using encode decode, the encode decode method for an altered path type, which is kind of an abelianized path type. But again, if you're interested, you can ask me about this later. Let me just summarize kind of the formalization instead. So the formalization is available online here. So here we have just under 10K lines of code, but it's not completely true because a lot of this is already in the Cubical library. So it's a bit hard to estimate exactly how much code we've written, but I think a reasonable thing would be to double this. So say 20 lines of code. It's 20,000 lines of code. The plan is, of course, to get everything merged into the Cubical library. And if you're interested in the work on CW complexes by Loic and me, this is already available in the library under cubical/CW. Did I say something else? Oh, yeah. Okay. There's one thing which I haven't mentioned yet, which people might be interested in. So now that everything has been formalized here, of course, this means that we should be able to plug in any fixed pi n sm into Agda and just compute a list of integers r naught up to rk such that pi n of sm is isomorphic to, well, z up to r naught and a bunch of these torsion guys. So we should be able to compute any homotopy group, right, of any sphere. Yeah, so I feel like I always use his face everywhere. Now this is online and recorded, so maybe well, yeah, you can imagine something I would put here. I've tried to run some computations, but I haven't been able to get anything out of it. So I tried with a sort of smallest possible example, which was pi2 of S2. I just wanted to use our formalized proof to compute the number of generators of this guy, but even that didn't terminate. So, the usual. Okay. Finally, some future work. This one thing I should mention is kind of improving this result. So technically, I mentioned this, we should be able to produce this list of integers and this isomorphism. So this list here and this isomorphism here. But actually, our proof only shows that this exists up to propositional truncation. Now, this is kind of the theorem, but you can actually escape this propositional truncation by proving that this is unique in the appropriate way. And what this essentially is the uniqueness is the uniqueness of the Smith normal form. So this we don't have in Cubical Agda yet. We have the uniqueness. Sorry, we have the Smith normal form, and this was used in the proof, but we don't have the uniqueness of it. So this is something we really should do. Hopefully, we'll do at some point to kind of beef up to formalization. But it's not crucial, but it would be cool to have. And with those words, I guess I should say thank you for listening.
Great, thanks very much, Axel. So we will use our visual applause or using the Zoom reactions.
Thank you.
And we have lots of time for questions. So if you want to ask a question, you can just unmute yourself. Well, I see Emily has a hand raised, so I'll let Emily go first.
Sure. So I didn't quite understand the implications of the last comment about that what you prove is the mere existence of generators. I mean, does that mean that you can't actually compute the explicit numbers, or what could you just clarify?
Yeah, I mean, so you're gonna compute them, but they're gonna be in the point constructor of the propositional truncation, right? So I mean, so if you normalize this in Agda, you're not gonna get R naught. You're not gonna get R naught R1 RK. You're gonna get prop trunk R naught R1 RK. So we can see it with our eyes, but what's supposed to be there, but it's gonna be wrapped inside of a propositional truncation. So that's the. So from our point of view, it's the same thing, but technically speaking, it is wrapped within a propositional truncation.
Right. So from a human point of view, if the point is to understand the answer,
yeah, exactly.
In theory, modular runtime issues, you do actually have the answer. It's just the answer is a term of a different type then.
Yeah, exactly. Yeah.
More questions? Well, I have a sort of a follow-up comment to the computability. I don't know the exact statements, but there are theorems saying that computing these homotopy groups is hard. Right? I think sharp P hard or something like that. So very hard. So we know there won't be some algorithm that's quick at doing this.
No, yeah, of course. Who wrote that paper actually?
I'm blanking on the name, but it's probably from the 80s or so.
Yeah, it's a double explanation or something like this. Right?
Yes, it was out of MIT back in the 80s, I think, but I forget the author. I'll send you a note. I also, I see a hand up. Steve, you go next, please.
But hard or not, this does produce an algorithm to compute them. So what other algorithms are known or have been done in the past, and how does, so is that a contribution here already to have such an algorithm? Whether it's a good one is a second question, right?
I guess it is well known that they are computable, right? I mean, for example, that paper that Dan mentioned now, that I'm forgetting the author of.
Ed Brown.
Oh yeah, right. Yeah. So there was definitely an algorithm, but however, the correctness of this algorithm, I guess, I'm not sure if the proof of the correctness of this algorithm is constructive, or if it even makes sense to talk about the proof of correctness of this algorithm. Yeah, so it depends on so an algorithm definitely existed, but I think having a formally verified algorithm. That's the key contribution here.
Yeah, so I mean, Ed Brown's paper was from 1957, I think, and it proved that the classical homotopy groups are computable, but it uses, I believe it uses simplicial methods. It's not something that's homotopy invariant like this proof is. So this is definitely an additional contribution, even just from the computability point of view.
Right.
I was curious. I have sort of a few related questions about the CW complexes and the weak Hurewicz theorem. So the first is a comment. The way Hatcher's textbook proves the Hurewicz theorem is by proving the weak Hurewicz theorem to compute the lowest homotopy group as a quotient as you specify, and then computing the homology and saying, hey, we got the same computation. So just saying that you're in good company in that approach. You're doing the same thing.
Okay, I didn't remember this being there. Okay, yeah, that's interesting.
Yeah,
we definitely looked in Hatcher for inspiration when picking the proof, but I guess we didn't really spot this. But okay, that's good to hear. We're in good company.
Yeah, okay. So then my question is, there's another class of spaces besides CW complexes. You can look at cellular spaces where you're allowed to attach the cells in any order. They don't have to go up in dimension. And some things are certainly easier there. Like I would imagine closure under pushouts is going to be easier and results like that. But then some things are more difficult, like knowing that the homology is finitely generated isn't something that's tautological from that point of view. So I'm just wondering if you considered using cellular spaces and whether that just doesn't work or you didn't think about it.
Now we didn't think about it, but it's a good question. I mean, we did towards the end of the project start thinking about more general classes of spaces than CW complexes, I guess, which I guess would include cellular spaces.
Yeah, it's the same set of homotopy types. It's just a more flexible presentation of them.
But so are you still? Sorry, yeah.
Oh, actually, I can also address that. So I actually also formalized some of, not all of the same results, including certainly not the Hurewicz theorem part, but for example, the closure of this class of spaces under pushouts, and it was exactly using the fact that you have two presentations, one by sort of finite CW complexes and the other by cellular spaces. And so the part that's difficult there is to convert a cellular space back into a CW complex, and that needs this kind of like, you have to be able to push low dimensional cells off of high dimensional cells, which is essentially the same kind of like cellular approximation argument you need in the proof to prove that CW complexes are closed under pushouts. So I can say that approach does work. I also ran into some interesting formalization issues where like, well, for example, a cell complex is a string of maps essentially, where each map is a pushout. And so you can represent that as a list of sorts, but you could either append to the end of the list or the beginning of the list. In other words, I could say a cell complex of length n is, I take a cell complex length, or n+1, I take a cell complex length n, and then at the end, I push on another map. Or you could say, I start with a map, a pushout, and then I compose with a cell complex length n. And it turns out the second one is much, much better. In the same way that it's maybe not too surprising for a computer scientist, because the way that computer scientists do induction of lists is also at the front of the list and not at the end of the list. So it's just like this. There's actually a formalization of this that's also available on the same repository, the CMU HoTT / Serre finiteness repository under the cellular branch, I guess. It's sort of hidden, but I proved enough theorems to convince myself that there were not going to be any problems with this approach. And then I guess independently, Axel and Loic had this more, this other approach that really only uses the CW complex presentation.
Is that where it is? I've been looking for this for a long time.
Yeah, it's hiding.
Okay, I see. Okay, but that's interesting. I want to ask you something about it. Oh, what did I? For then for CW complexes, you used this recursive definition, right?
Yeah.
Right. And how did you define? So how did you define cellular spaces?
I think something like a cellular complex of length n is, or sorry, of length 0 is. Maybe you also want to do a relative version, but oh wait, maybe I have to do relative. Maybe I should just look at my formalization. You might have to do a relative version where you start with some A and you sort of have a string of n maps. Okay, so if the cell complex of length 0, there's just one of them, and then a cell complex of, based on a given A, and then a relative cell complex of like n+1. I have some class of cells, and so I take a map from A to B, which is a push out of one of those cells in its specified way. And then I give you a cell complex of length n based on B.
Mm-hmm.
And then you can define the realization to just be sort of the last space.
Mm-hmm.
I didn't consider ever any kind of infinite cell complexes. This didn't seem, I think if you wanted to, because in your formalization, you also consider like CW complexes that are with still only finitely many cells per dimension, but might be infinite dimensional. And that I think is going to pose serious problems for the cellular approach, because you need to index by some kind of like transfinite. It's very important that you can just attach one cell at a time. I don't know. Because, for example, also in your proof, you weren't able to prove the push outness unless like A was finite and so on. So
yeah, right.
So that's another.
Yeah, I guess you need to index by something that's kind of projective. Yeah.
Yeah, right. And so we just use a finite, or I used a finite word.
Well, yeah. And I guess the only projectives are the finite ones,
Yeah,
right?
right.
In this time. Yeah. Okay. No. Okay. I forgot about this. I think.
Does anyone else have any questions?
Can you go back to some of those slides you skipped toward the end about formalization?
Yeah.
I forget where, I think maybe lesson 3. Yeah, here.
Yeah.
Sorry, can you say something?
Yeah, sure. I was just trying to remember what I written. Yeah, right. So here, right, there is this kind of obvious way of defining CW complexes, as you would do if you're a normal computer scientist, at least, which is this like nice recursive definition where you define. I mean, you had in the data that goes into a CW complex, you have this push-out diagram, right? And so you can define them recursively by saying that the n+1 skeleton literally is the push out of some map from the n-1 skeleton. And then you get that this push out equation, like the statement that the n+1 skeleton is the push out of the n skeleton, that's going to hold definitionally. And that's a really nice property to have. But that definition, first of all, only limits you to finite CW complexes, and so it's less general. And we thought that it was less flexible too, because it was less general. In the end, it kind of became less flexible. So we wanted to do things like with taking a CW complex and just swapping one of the stages in it, and that was really hard here, because as soon as you modify something, everything on top of it is going to be modified because it's recursively defined. So in the end, what we did was, I mean, I'm a very lazy person, so I was still tempted to go with this one because I love definitional equalities and probably rely on them a bit too much in my life. But we realized that actually you can kind of have your cake and eat it by just defining sort of a strictification function from CW to CW, which takes a CW complex and spits out something that's equivalent, but it's kind of a strictified version where you actually force the push out squares to be strict. And you can actually play this game with like a lot of the data that pops up here. Is you can also, if you look at like maps between CW complexes, if you first strictify your complexes, then you can also strictify the maps between them so that certain squares commute definitionally. And like this is a really neat game that we played quite a lot in the formalization. I think computationally it's absolutely horrendous what's going on here. So that's probably not good for actually computing anything in the end later when we try to compute homotopy groups. But from the point of view of a lazy formalizer, this was a really sort of nice insight for me that we can strictify things and still be general sometimes, at least.
I see a question in the chat. I don't know if you can see that yourself, Axel.
Yeah, I can see it.
And I'll just mention the question in the chat mentions Kenzo, and I don't know if people here know about Kenzo, but it's an amazing program written in the 90s in Lisp, which computes homotopy groups of iterated fibers and loop spaces and spheres and so on, and does it remarkably efficiently. Uses the implicitly something equivalent to the Serre spectral sequence. It's not quite working with the spectral sequence. And so the question is about whether you could maybe try to get something with similar efficiency, with some of the ideas mentioned in this comment. Manually giving a matrix of the mapping degrees, proving it coincides with the one in the construction.
Yeah, something like this sounds, I mean, it's always hard because there's always so much hidden in the formalization that you think is kind of true, but then in the end, Agda starts evaluating it. And but I agree that the in principle, yeah, this sounds like a reasonable thing. And I think this was kind of, I mean, when we started doing this work on CW complexes, this was kind of the justification of this whole project was doing something similar. Although that never really came to anything, but it might in the future. But I think that's
well, when you start with a sphere, there is no matrix to give because there's only one non-trivial cell. So
yeah, that's true. That's true.
So that might hinder that idea, but
yeah, I guess I was still thinking about homology now, and in general, I was stuck in cellular homology. But yeah, no, okay, sure. For the homotopy group of spheres, it's more tricky, of course.
Anyway, I'm glad Kenzo was mentioned because it is a pretty remarkable program. You can use it today within Sage. You can import Kenzo and run computations. I had one more question.
Oh, yes, yeah.
Your definition of Hurevich connected. Maybe you can flip to that.
Yeah, I'm kind of regretting using Agda code for this one, but yeah, it will look nice in my head. This one, yeah.
Yeah, so I'm curious why you need more than the first condition. Like if you insist that the lower skeleton vanish or contractible, don't you know that the nth skeleton has to be a wedge of spheres and the next one has to be a cofiber?
Absolutely. This was just me being overly explicit, but yeah, from this data, of course, you can prove this, which then gives you this. There's a little bit of a subtlety, I think. What's the subtlety? You need to prove that. I think you need your attaching maps, at least in dimension n+1 and n+2, to be pointed. But yeah.
But they're mapping into a contractible. Well, in dimension n+1, they're mapping into a contractible.
Absolutely, yeah. But then the one after that, I think you need to. You need a, but this is since everything is connected enough, and we're just proving that this is supposed to merely exist. This is never a problem in practice. But it's a tiny bit stronger, I think.
Right.
Because of it. But it's still, I really only wrote this out for sort of clarity. I mean, the key thing I'm using really is this the last bit actually, like this guy being a cofiber of such maps.
Okay, any last questions? Okay, let's all thank Axel again.
Thank you.
Oh,
Thanks
and
for
next week
listening.
we have Stefania D'Amato, who will, actually I forget her title, but she'll be speaking. Oh, she hasn't told us her title yet, but she'll be speaking in 2 weeks. Okay, see you then.
Yeah.